Artificial intelligence and machine learning have made tremendous progress in the past few years, including the recent launch of ChatGPT and art generators. But one thing that is still outstanding is an energy-efficient way to generate and store long and short-term memories at a form factor that is comparable to a human brain. That is until now. A team of researchers in the McKelvey School of Engineering at Washington University in St. Louis has developed an energy-efficient way to consolidate long-term memories on a tiny chip. The Preston M. Green Department of Electrical and System Engineering's Clifford W. Murphy professor, Shantanu Chakrabarty, and members of his lab created a relatively easy-to-use device that mimics the dynamics of the brain's synapses, connections between neurons that allow signals to pass information. While human brain synapses may be able to retain complicated memories due to an intricate interaction between numerous chemical paths, the artificial synapses employed in many current AI systems are very basic. The research team led by Chakrabarty demonstrated that parts of these dynamics, which enable AI systems to continually learn new tasks without forgetting how to carry the old ones out, can be mimicked by artificial synapses. In order to do this, Chakrabarty's team created a system that functions as two connected reservoirs of electrons, with an artificial synapses, or junction, allowing electrons to move between the two reservoirs. They employed quantum tunneling, a process that allows an electron to seemingly travel through a barrier to make that connection. They employed a technique called Fowler-Nordheim quantum tunneling, in which electrons leap over a triangle barrier while also altering the geometry of the barrier. Compared to current connections that are too complicated for computer modeling, FN tunneling offers a connection that is more simplified and more energy efficient. The beauty of this is that we can control this device up to a single electron because we precisely designed this quantum mechanical barrier, Chakrabarty said. Chakrabarty and doctoral students Mustafazur Rahman and Subankar Bose designed a prototype array of 128 of these hourglass devices on a chip less than a millimeter in size. Our work shows that the operation of the FN synapse is near optimal in terms of synaptic lifetime and specific consolidation properties, Chakrabarty said. This artificial synapse device can solve or implement some of these continual learning tasks where the device doesn't forget what it has learned before. Now, it allows for long-term and short-term memory on the same device. Chakrabarty said because the device uses only a few electrons at a time, it uses very little energy overall. Most of these computers used for machine learning tasks shuttle a lot of electrons from the battery, store it on a capacitor, then dump it out and don't recycle it, Chakrabarty said. In our model, we fix the total amount of electrons beforehand and don't need to inject additional energy because the electrons flow out by the physics itself. By making sure that only a few electrons flow at a time, we can make this device work for long periods of time. The work is a component of the study Chakrabarty and his lab colleagues are conducting to improve sustainability of AI, with the next generation of models needing about 200 terajoules to train one system. The energy needed for present AI computations is increasing rapidly. Furthermore, these systems fall well short of the capability of the human brain, which has around 1,000 trillion synapses. Right now, we are not sure about training systems with even a half a trillion parameters, and current approaches are not energy sustainable, he said. If we stay on the trajectory that we are on, either something new has to happen to provide enough energy, or we have to figure out how to train these large models using these energy-efficient dynamic memory devices.